Hidden inside the world's most advanced rockets is a metal most people have never heard of: scandium. Tiny element, extraordinary mission.
Imagine a ghost, but not the kind that haunts an old house. Think of a ghost material, like an element that is hiding in over 800 different places all around you, right under your feet.
Right, but it's so incredibly elusive that it's practically invisible to traditional mining.
Yeah, exactly. But here is the kicker. If you manage to capture just a microscopic pinch of this ghost and, sprinkle it into everyday metal, it acts like pure magic. It transforms that ordinary metal into impenetrable aerospace-grade armor.
It is the absolute definition of a scientific paradox. I mean, you have a substance that is simultaneously everywhere and nowhere, and yet it dictates the very limits of what is physically possible in modern engineering.
It really does. Welcome to today's deep dive. We are unpacking the story of element 21 on the periodic table. We're talking about scandium.
And this isn't just a chemistry lesson. It's a century-spanning detective story about, well, the literal bottleneck of tomorrow's technology.
We are going to explore how this single ghost-like metal builds our modern world. From the spacecraft taking us to the stars to the high-efficiency fuel cells powering our energy grids.
But before we get into how scandium builds rockets today, we have to travel back to a time before anyone had ever actually laid eyes on it.
We're heading back to the 19th century, right? Looking at the work of the Russian chemist Dmitry Mendeleev.
Yeah, exactly. When Mendeleev was assembling his famous periodic table, he wasn't just organizing the known elements. He was looking at the fundamental mathematical and chemical rhythm of the universe.
Okay, so he's arranging elements by their atomic mass and chemical properties.
Right, and when he looked between calcium and titanium, he noticed the sequence just skipped a beat.
Because calcium has an atomic weight of roughly 40, and titanium is around 48. So Mendeleev just looks at that gap and assumes something is missing.
Well, he did far more than assume. He looked at the trends in the surrounding elements and calculated exactly what that missing piece should look like. Yeah, he confidently asserted the existence of a missing element he called ecoboron. He predicted its atomic mass, its density, and even how it would react with oxygen.
That is just wild. It's like throwing an elaborate dinner party and leaving one specific empty chair at the table because you mysteriously know the exact dimensions, the height, the weight, and the precise personality of a guest who hasn't even been born yet.
That is a perfect way to put it. For Mendeleev, if the sequence skipped a beat, it didn't mean the rhythm was broken. It just meant humanity hadn't found the instrument playing that specific note yet.
So the empty chair just sits there until 1879.
Yep.
And that's when a Swedish chemist named Lars Fredrik Nilsson is studying rare earth minerals from Scandinavia, specifically two incredibly complex minerals called euxenite and gadolinite.
And through his extraction processes, Nilsson finally isolates a brand new oxide.
Mendeleev's ecoboron finally gets a physical presence.
Exactly.
Yeah.
And Nilsson chose a deeply patriotic naming convention. He called it Scandium, in honor of Scandinavia, where those host rocks were discovered.
Going from a theoretical phantom on a piece of paper to a physical reality pulled from freezing rocks is an incredible leap. I mean, let's talk about what Nilsson actually found. Let's look at the anatomy of element 21.
Sure. So on the periodic table, it sits right at atomic number 21. It's categorized as a transition metal located in group 3 and period 4 with an atomic mass of 44.9559 atomic mass units.
Okay, and the sources mention its electron configuration is argon in brackets, followed by 3d1, 4s2.
Right.
But what does that actually mean for the material? Why do we care about where its electrons are?
Because that is the secret to its behavior. The 3d1 part is crucial. Scandium is the very first element in the periodic table to have an electron in the d orbital.
Okay.
And that d orbital gives transition metals their unique ability to share electrons fluidly with other elements. It is the molecular foundation that allows scandium to form such incredibly strong, versatile alloys.
Okay, so if you handed me a solid chunk of pure scandium, what am I actually looking at?
Visually, it's quite beautiful, actually. It is a silvery white metal, but it has this very subtle, surprising yellow or pink tint to it.
A pinkish metal sounds kind of delicate, especially since we know this is used in aerospace manufacturing.
Well, there is a surprising truth to that. Pure scandium is actually softer than most people expect. We associate aerospace metals with unyielding rigidity, but in its pure, unalloyed state, scandium has a bit of give.
But its thermal properties are a completely different story, right?
Oh, yeah.
Because it doesn't melt until it hits a blistering 1,541 degrees Celsius, and it won't boil until it reaches an astonishing 2,036 degrees Celsius.
That thermal stability is just staggering. And chemically, it commonly forms a +3 oxidation state, dissolves readily in acids.
Right.
But one of its most brilliant evolutionary quirks happens when it meets regular air. When exposed to oxygen, scandium slowly develops a yellowish oxide coating.
Oh, like rust on iron.
Actually, the opposite mechanism.
Ugh.
Yeah. When iron rusts, the iron oxide expands and flakes off, exposing more fresh iron to be destroyed. But with scandium, the oxide layer forms a perfectly sized, impermeable skin.
So it acts as a shield.
Exactly. It completely protects the pure metal underneath from further degradation. It's basically a self-protecting metal.
Okay, wait. I'm looking at this list of minerals in the sources. Thortveitite, wolframite, gadolinite. It says scandium is found in over 800 different minerals.
Yes, it is.
If it is sitting in 800 different places, how can it possibly be considered one of the rarest transition metals on Earth?
Ah, that is the rarity paradox.
Yeah.
It is not rare because there is a low total quantity of it on the planet. It is rare because it is almost never concentrated in one place.
Oh, I see.
Yeah, it virtually never occurs as a pure standalone metal in nature.
So it's like taking a single teaspoon of sugar and stirring it into an Olympic-sized swimming pool.
That's a great analogy.
The sugar isn't missing. It is definitely in the pool. But if you asked me to go retrieve that teaspoon of sugar for your coffee, I'd have an agonizingly difficult time filtering millions of gallons of water to get it back.
Exactly. And that dispersion creates an absolute extraction nightmare. You cannot just set up a scandium mine. There are no rich veins of scandium ore to dig out of a mountain.
So we're completely reliant on finding it as a byproduct.
Mostly, yes. Today, scandium is painfully recovered while we are mining for other things, like titanium, uranium, rare earth elements, and nickel.
Wow.
During the intense, complex chemical processing required to refine those primary metals, engineers have to meticulously scrape off and recover tiny, trace amounts of scandium from the waste streams.
So we are moving mountains of earth to mine uranium, just hoping to catch a few grams of this ghost metal in the filter.
Pretty much.
That makes it incredibly labor-intensive and wildly expensive. Which brings up the obvious question. If it is this agonizingly difficult and expensive to extract, why does the aerospace industry obsess over it?
The answer lies in metallurgy. In a process that almost feels like modern alchemy, it is all about what happens when you combine it with aluminum.
Ah, the magic pinch. The sources note that adding just a tiny fraction of a percent of scandium to aluminum transforms it completely. But how? What is actually happening inside the metal?
So when you add that microscopic amount of scandium to molten aluminum, the scandium atoms don't just float around randomly.
Okay.
As the metal cools, they form these incredibly stable microscopic compounds called Al3SC precipitates.
Like little atomic knots tying the metal together.
Think of it like adding rebar to concrete. When you put physical stress on standard aluminum, the distinct layers of atoms want to slide past one another.
Right, and that sliding is what causes metal to bend, deform, or break.
Exactly. But those scandium precipitates pin the grain boundaries in place. They act as microscopic roadblocks that physically stop the atomic layers from sliding.
So the scandium is literally preventing the aluminum from tearing itself apart at the microscopic level.
Yes.
That explains why the resulting alloy is vastly stronger, remarkably lighter, and highly resistant to corrosion.
And in aerospace engineering, that is the holy grail.
Yeah.
Engineers use this exact scandium aluminum alloy to construct the frameworks of spacecraft and rockets.
Because when you are trying to escape the Earth's gravity, weight is your absolute worst enemy.
Right.
Every single ounce of weight you can shave off a rocket's fuselage without losing structural integrity saves massive amounts of rocket fuel. Or it allows you to pack an extra piece of scientific equipment or more oxygen for the crew.
Exactly. The fuel savings alone make the astronomical cost of the scandium totally worth it.
But the desire for lightweight strength isn't just limited to the vacuum of space, is it?
Not at all.
Which is one of the funniest juxtapositions in these sources. The exact same scandium aluminum alloy trusted to survive the violent forces of a rocket launch is heavily utilized at your local sporting goods store.
It really is.
It is used to build high-performance bicycle frames, golf clubs, and lacrosse sticks.
And baseball bats.
Yes, you are swinging a bat made of the same stuff that goes to Mars just to hit a fastball a few milliseconds quicker. There is something profoundly absurd and wonderful about bringing literal rocket science to a weekend baseball game.
It proves how universal the physics of efficiency really are. Less weight and more strength is always a winning combination.
Mm.
But, scandium is highly versatile, well beyond its relationship with aluminum. It forms incredibly stable compounds on its own.
Right, like scandium oxide, scandium fluoride, and scandium chloride, Se2O3, SCF3, SCCl3. Where are we actually interacting with these?
Well, one of the most visible places is right above our heads. Scandium iodide is a crucial component used in metal halide lamps.
Oh, the massive high-intensity lights used to illuminate sports stadiums at night.
Those exact ones.
Hmm.
And the high-intensity lighting used in professional television and film production.
Interesting.
Yeah, when you vaporize scandium iodide inside these lamps, the scandium atoms become excited and emit light across a very broad spectrum. It beautifully replicates the exact spectrum of natural bright daylight.
So even if you aren't swinging a scandium baseball bat on the field, if you are watching a night game on TV, you are seeing the players clearly because scandium is tricking the camera into thinking it is daytime.
It's all about manipulating the physical environment. And that brings us to how scandium is quietly revolutionizing the energy sector, specifically high-temperature solid oxide fuel cells.
Right. A solid oxide fuel cell, or SOFC, is a device that converts chemical energy from a fuel directly into electricity at very high temperatures. It's incredibly efficient.
Very.
But the sources highlight that these cells use something called scandium-stabilized zirconia. How does scandium actually improve a fuel cell?
It comes down to the crystal lattice of the zirconia. Inside the fuel cell, you have an electrolyte, and its job is to allow oxygen ions to pass through it to create the electrical current.
Okay.
But it operates at extreme temperatures, which creates massive physical stress.
So we need the oxygen to move, but the material needs to hold up to the heat.
Exactly. Normally, engineers use yttrium to stabilize the zirconia lattice. But scandium atoms are the absolute perfect size for this job.
Oh, wow.
Yeah, when you swap them into the zirconia structure, they essentially prop the molecular doors open wider. They dramatically improve the electrical conductivity by giving the oxygen ions a much smoother path.
Which allows the fuel cell to operate at lower temperatures while remaining highly efficient and lasting significantly longer.
Right. And it is not just energy. Scandium is becoming a major player in metal additive manufacturing.
Which is 3D printing with metal.
Yes, 3D printing metal is notoriously difficult. You are rapidly heating a tiny spot of metal with a laser to melt it, and then it cools almost instantly.
That sounds like a recipe for cracking.
It is. That extreme temperature fluctuation causes intense thermal gradients, which often leads to microcracking at the grain boundaries. The printed part just tears itself apart as it cools.
But if we go back to the rebar analogy, does the scandium step in to fix the crystallization?
It forces the metal to crystallize perfectly. The scandium provides uniform nucleation sites.
Okay, so it acts like a blueprint.
Basically. Instead of the metal solidifying randomly and cracking, the scandium acts in the template, guiding the molten metal to form incredibly fine, uniform grains. It allows engineers to 3D print complex, lightweight, and virtually indestructible parts layer by layer without the fear of structural failure.
It is the secret ingredient in almost every futuristic technology we have. But before we assume this element is interwoven into the fabric of life itself, there is a fascinating biological note in the sources.
Yeah, this is interesting.
Despite scandium being literally everywhere hidden inside those 800 different minerals in the Earth's crust, it has exactly 0 known essential biological function in humans.
None. It exists in our environment in trace amounts, and it occasionally finds its way to the food chain, but our bodies completely ignore it.
We just don't use it.
We don't use it, and we don't need it to survive.
Its entire story is purely about human engineering. It is a material waiting to be manipulated by our ingenuity. Which brings us to a critical crossroad. We know what scandium does today, but we need to look at why it is the literal bottleneck for the technology of tomorrow.
The global trajectory of human innovation is pointing entirely toward weight reduction and energy efficiency.
Right.
We are demanding lighter aircraft to significantly cut carbon emissions. We are expanding deep space exploration, which requires materials that can survive the harshest environments imaginable.
We are pushing for the mass global adoption of electric vehicles, too.
Yep. And we're relying on advanced hydrogen fuel cells to stabilize our power grids.
And in every single one of those industries, weight and resistance are the enemies. If you save just a few pounds on the frame or the battery casing of an electric vehicle, that EV can drive significantly further on a single charge.
Exactly.
The math just demands materials that are lighter and stronger.
Which means the demand for scandium aluminum alloys and scandium stabilized fuel cells is surging, but we hit a hard wall.
Because it's so hard to get.
Right. The future relies on this element, but it remains incredibly rare, scattered like sugar in a pool, and agonizingly expensive to extract as a byproduct.
So if the EV and space industries scale up the way they plan to, do we even have enough? What happens when we need tons of this ghost metal, but we are still meticulously scraping grams of it off the filters of uranium mines?
That is the multi-billion-dollar bottleneck, and it has sparked a massive global scientific hunt.
Let me guess, they aren't looking for new scandium mines.
No, because they know concentrated veins don't exist in the Earth's crust. Instead, they are racing to develop cheaper, highly innovative ways to extract scandium from places we previously threw away.
You mean industrial waste?
The tailings and the runoff from older existing mines, places like the red mud left over from aluminum production, or the acid waste generated from titanium dioxide
Oh,
manufacturing.
wow.
These massive industrial waste streams actually hold significant amounts of dispersed scandium.
So the race is on to develop chemical processes that can efficiently filter out that teaspoon of sugar from the toxic waste we've already dumped.
Exactly.
Whoever cracks the code on cheap, efficient scandium extraction from red mud won't just make a fortune. They will literally dictate the pace of the next generation of aerospace and energy technology.
They hold the keys to the future.
When you look at this entire journey, Element 21 really is the ultimate underdog. It begins as a ghost, an empty box left on a table by a 19th century visionary who just trusted the mathematical rhythm of the universe.
Yeah.
Then it gets pulled from freezing rocks, only for humanity to realize the Earth grounded up and scattered it so sparsely we can barely gather it.
The universe provided the absolute perfect ingredient for us to build our future. A metal that withstands blistering heat and reinforces aluminum to pierce the atmosphere. But it didn't put it in a convenient pile.
It definitely didn't.
It forced humanity to evolve our science, our chemistry, and our sheer willpower to figure out a way to piece the puzzle together.
That is what makes this so fascinating. But it also raises a massive question for you to mull over today. If the violent, chaotic formation of planet Earth is what caused scandium to be ground up and scattered across 800 minerals, what about the rest of the solar system?
Oh, that completely reframes how we look at space exploration.
Exactly. What if near-Earth asteroids, which formed under very different conditions, contain concentrated veins of scandium?
That would change everything.
We are desperately trying to build lightweight rockets to get into deep space, but deep space might be the only place where element 21 is actually concentrated. The very metal we need to conquer space might be waiting for us on an asteroid.
Meaning, space travel could be the exact thing that unlocks more space travel.
Yes.
It creates a beautiful loop. The element that gets us to the stars might be waiting for us when we arrive.
The next time you look at a piece of ordinary aluminum, a soda can, a window frame, or a bicycle, imagine what it could be. Imagine its potential if it were just touched by a microscopic pinch of element 21.
It's amazing to think about.
Scandium is just one brilliant piece of the universal puzzle, and we have only scratched the surface of the periodic table. If element 21 can build rockets from ghost and industrial waste, what profound, world-changing mysteries are quietly waiting in the very next element of the Atomic 118 series? We will catch you on the next deep dive.